From the fuel in your car to the medicine in your cabinet, pretty much everything we use is made in these huge, complex chemical plants. But here's the thing. Behind all that steel and piping, there's a hidden digital world, a kind of invisible blueprint that makes it all work. And today, we're going to dive right into that world. We're talking about process simulation. So let me ask you a question. Let's say you're in charge of building a brand new chemical factory. And the price tag? We're talking billions of dollars. So how do you know your design is actually going to work, right? You can't just, build it and cross your fingers. The stakes they're incredibly high. And that right there is the billion-dollar question for chemical engineers. See, you're not just building one machine. You're designing this incredibly interconnected system. And the cost of a mistake? Oh, it's not just financial. It can be a massive safety risk, a huge environmental problem. Okay, take a look at this. This is what's called a process flow diagram. It's basically the map of the factory. You've got reactors, distillation columns, heaters, compressors. I mean, look at it. It's all linked together. And a tiny miscalculation in just one of those parts could cause this disastrous chain reaction through the whole system. So yeah, you have got to get it right, long before a single piece of steel is ever put in place. So how on earth do they pull this off? Well, the answer is kind of mind-blowing. They build the entire factory first, but they do it virtually. Before anyone even breaks ground, engineers build a complete, functioning digital twin of the plant right inside a computer. And that is the world of process simulation. All right, now it's super important we get a couple of terms straight. There's process synthesis. Think of this as the creative what-if stage. It's like an architect sketching out a wild new idea for a building. But then there's process simulation, and that's what we're focused on today. This is the will it work stage. It's where you take that blueprint and you really put it to the test, asking that crucial question. The whole goal is to predict exactly how it's going to perform. So what is it really? At its core, process simulation is all about building a mathematical model of the process. You feed this incredibly complex model into a computer, and the computer just crunches through all the equations that describe how all the materials and energy are going to move through the system. And what you get out the other side is a precise prediction of what will happen inside your virtual plant. Here's the best way to think about it. It's like a flight simulator, but for a chemical factory. Seriously, a pilot uses a simulator to test the plane's limits in a totally safe environment, right? Well, an engineer does the exact same thing with a process simulator. They can throw different conditions at it, push the system to its breaking point, tweak it for peak performance, all without a single drop of real-world risk. It's a total game changer. Okay, so when you're facing a problem this massive, where do you even start? I mean, you can't just start dragging and dropping virtual pipes and hope for the best. No way. Engineers need a roadmap, a structured plan to guide them, and the one they use is absolutely brilliant. It's called the onion design model. The whole idea is actually pretty simple, but it's totally revolutionary. The model tells engineers to design the whole process in layers, like an onion. You start from the most critical part, the core, and you work your way out. And this inside-out approach is the secret sauce. Why? Because it forces you to solve the biggest, most fundamental problems first. That way, you don't discover some catastrophic flaw only after you've already planned out the entire thing. So let's peel back these layers, shall we? You start right at the heart of it all, the reactor. That's where the actual chemical reaction happens. If you nail that, you've got a solid foundation. Okay, next layer out. You've got to separate your final product and recycle anything that didn't react. Then, you design systems to recover heat and save energy, super important. After that, you add the utilities. Think boilers, cooling towers, that kind of stuff. And then finally, the very last layer is waste treatment. See, it's this perfectly logical journey from the core function all the way out to the support systems. All right, so theory is one thing, but let's make this real. Let's look at how this all works in practice, with an actual example from our source material, making something called N-octane. It's a component in gasoline. And here we are again, back to this complex diagram. This time, it's for making that N-octane. This right here, this is the finish line. The whole goal of the simulation is to get this entire process running perfectly inside the computer, predicting every temperature, every pressure, every flow rate at every single point in the system. But, and this is key, they don't try to build this whole thing at once. That would be a nightmare. Following that onion model, they build it in stages. So first, they just simulate the reactor. That's it. Make sure the chemistry works. Then, they add in the distillation column to simulate how they'll separate everything. And only then do they connect the recycle loop to see how the whole system behaves when it's all connected. This technique actually has a name. It's called the sequential modular approach. And honestly, the best way to think about it is like building with digital Legos. You build and solve one module, one piece of the factory, at a time. Once you know that piece is working perfectly, its output just becomes the input for the next piece in the chain. It's a really smart, methodical way to build up something super complex while making sure every single step is accurate along the way. Now, you might think that with software this powerful, the computer does all the work, but that's not the whole story. Building a great simulation, well, that takes more than just fancy software. The real skill is in the hands of the engineer, and over the years, the industry has come up with a set of, well, let's call them golden rules to get it right. And these rules are absolutely crucial. First off, have a clear goal. What question are you trying to answer here? Are you trying to make more money or make the plant safer? You can't do it all at once. Second, you have to draw a boundary around your system. You need to know exactly what's in your model and what's out. It's the only way to avoid mistakes. Third, and this might be the most important one, start simple. Get the basics working before you start adding all the complicated stuff. And finally, you have to always double-check your results. A simulation is worthless if it doesn't match reality. You know the saying, trust but verify? So when you boil it all down, what's the big takeaway? Well, process simulation is so much more than just some clever software. It's the virtual blueprint. It's what allows us to design, test, and perfect the unbelievably complex processes that safely and efficiently build the modern world all around us. And that really leaves us with a pretty mind-bending thought, doesn't it? We've basically mastered building virtual factories for things like chemicals and fuels. So as this technology gets even more powerful, what's next? What other incredibly complex systems will we be able to design and test in the virtual world? Honestly, the possibilities are just endless.